This is one of 4 talks about folding and unfolding. I'll give the first 2 today and tomorrow, and Joe O'Rourke will give the next 2 on Friday and Saturday. So this is folding hour, and you'll have one for the next 4 days. I wanted to give you a little bit in general what folding is all about, and then today will be all about linkages, or some about linkages. Because of the projector, you'll have a little bit of exercise in the information content of English. You have to guess the first stroke of every title. So folding, you have some geometric object. You want to know how it can reconfigure. And folding problems come up all over the place in the real world, in the scientific world, outside mathematics. This will be the main slide about applications of folding, because we're mostly interested in the mathematics. But there's lots of stuff behind here which you can ask questions about. We're going to talk about 3 different kinds of objects: linkages, pieces of paper, and polyhedra, and I'll get to exactly what they are. But you can think of a linkage as like a robotic arm. This is the Canada arm. I'm, in some sense, Canadian, so I have to put up a figure of that. You've got proteins, which are in some sense linkages. We'll talk about that at the end today. Paper folding, for example, airbags are very much like paper, except nylon. And minor difference, but they fold roughly the same way. And you've got to take this big polyhedron and make it flat to fit in the steering wheel. And when it expands, it shouldn't hurt the person that it's trying to save. Paper folding has also had applications in space deployment. You want to make a really big telescope lens. This is twice the size of the Hubble. It doesn't fit in a space shuttle because the space shuttle is pretty vertical. And so you fold it. You make lots of little pieces and fold it by some rigid motions. And then it can fit on the space shuttle. It goes out into space. It expands. Polyhedra unfolding. You have a polyhedron like this boat. Here is a very practical polyhedron. You'd like to build it, but you only have flat sheet metal. And so you cut it into pieces, unfold it into these flat shapes, cut each of these out of your sheet metal, and then bend it up into the real thing. And look, the boat floats, so it works. So this is sort of the application motivation of folding and unfolding. Now, what are the mathematical questions that come out of all of these folding problems? Well, in general, you have some object, either a linkage or a piece of paper or a polyhedron. You define some constraints about how it's allowed to fold. And then you want to know, well, what shapes can you fold? What are the limits of folding? Are there good algorithms for folding, or is it computationally intractable? The sort of constraints you get, just to give you an idea, with linkages, I haven't told you exactly what one is. We'll get there. You have to preserve these edge lengths, and the edges aren't allowed to cross each other, typically. Of course, these constraints can vary for different problems. So that's a simple linkage motion. We'll see a whole bunch today. Paper is similar. You have to preserve distances along the surface of the piece of paper, and it's not allowed to cross itself. If you've ever tried to fold paper, it's pretty hard to self-penetrate. And so, for example, if you take a square piece of paper that's white on one side and black on the other side, this is a folded over corner. You can fold, I don't know, for example, a zebra. Or at least in principle, you can fold a zebra. I can't. And I've tried. It looks pretty ugly when I fold it. And lastly, for polyhedra, and this is what Joe will be talking about, there's 2 sort of main polyhedron folding problems. One of them is unfolding. I give you a polyhedron like this cube. You cut along its surface, like along these red lines, and you want to unfold it into the plane without overlap. So this is a standard cross unfolding of the cube. And of course, you can go in the reverse direction, too. Given a polygon, what polyhedra can you fold? So that will be the topic Friday and Saturday. And these will be the topics today and tomorrow. This is the overview. You are here, and you know what to look forward to. OK, so now we're going to go into linkages. I will talk quickly, because there's a lot of stuff I want to cover. But feel free to stop me, slow me down, ask questions, whatever. Any questions yet? Good. No technical meat yet, so no questions. This is basically to tell you how far along in the talk I am. This slide will come up with a different pink item At this point, they probably won't mean very much. I'm going to talk, some of you know rigidity. I know I've seen a few familiar rigidity faces. Not many people know rigidity, but it's a very interesting kind of folding, so I thought I would sort of tell you about it, because it should be better known. It's very powerful. Then I'll talk about the pursuit of the locked chains, the quest for locked chains, and some latest stuff in algorithms. And then I'll talk about what I know about protein folding, which is still very, very early. So I should finally define a linkage for you. You can think of it as a graph where the edges have specified lengths. Those represent the lengths. The lengths of those edges are fixed. And then you imagine embedding that graph in the plane or in 3 dimensions or wherever you like. The edges are called bars. They're also called links. They're also called edges. There's lots of terminology around. I will try to stick to bars and vertices, but you know, if Joe were giving this talk, he would always call them joints and links. And you know, if someone else gave the talk, they'd use their own favorite terminology. There's no consistent terminology, I'm afraid. And then there's a few special kinds of graphs we're interested in. In general, you just have any graph. You can have crossing edges, whatever you want. An open chain or an arc is when the graph is a path. A closed chain or a cycle or a polygon is when the graph is just a cycle and a tree is a tree. Okay, this one at least only has one name. And now we're interested in how these things fold. So we should define configurations. A configuration of a linkage is just a placement of the vertices in your ambient space in the plane, let's say. And we particularly distinguish when none of the edges cross. This tends to be a useful distinction. Here, the edges aren't crossing. Here, the edges are crossing. Okay. Now we get a little fancier. We talk about motions. So if you can imagine this linkage, which is going off the screen, we've got one bar here and another bar here. This linkage can fold in 2 different ways. You can rotate about this hinge, so that's specified by this angle theta 1, and you can rotate about this hinge theta 2. For each pair of angles, it's any pair of numbers between 0 and 2 pi, that gives you some configuration of this linkage. And that's represented by this square. This is theta 1 and this is theta 2. And now this linkage, which is also drawn here, is embedded, let's say, in the space that has obstacles. And you're interested in how it can fold while avoiding the obstacles. So the whole thing, this square is called, it's not actually a square, it's a torus, right? And if you've played enough video games, you know you can embed the torus on a square where you wrap around up and down. Right. So the whole square is called the configuration space. The free space are the ones that where the linkage doesn't self-intersect and doesn't hit the obstacles. And if you look at a path in this space, that's interesting because it defines a motion of your linkage, and that's depicted by this diagram. Okay, so that's motion sort of in the very formal sense. Of course, you understand what it should be. It's just a continuum of configurations. Linkages go far back. I don't want to say too much about history. One of the earliest linkages is in 1784, this Watt linkage. The goal here was to take circular motion and turn it into linear motion, okay, like you use in steam engines. And, oh, the other way around. Oh, that's right. You have something going this way, and you want it, well, it's symmetric. It's invertible. Good. This is something that doesn't quite work, but it's pretty good. You can see this is almost straight, given enough lenience. And then the first linkage to actually do this conversion, this is the circular motion around here, and this is the linear motion, this vertex. I won't try to pronounce that because it'll show how poorly I know French. And there's a whole bunch of linkages for drawing straight lines, is a cute way to put it, with circular motion. I don't want to go into them except to say this is sort of the origin of the area. People really wanted to do this in mechanics, and that started this area. Instead, I want to turn to some meat. So let's look at rigidity. So rigidity is sort of the simplest question you can ask. I give you some linkage, and I just want to know, can it move at all from this position? So I give you a linkage and a configuration of that linkage. I draw it in the plane, let's say. Can this thing move? If it can't move, it's called rigid. If it can move, it's called flexible. That's it. Just has to move a little bit. It's a very natural question. There are lots of simple things you can prove, like if you have a triangulation in the plane, it's rigid. If you have what's called a pseudo-triangulation in the plane, it's also rigid. Pseudo-triangulation, every face has exactly 3 convex vertices, but it can have as many reflex vertices as you like. Turns out if you take a certain kind of pseudo-triangulation, remove one edge, it's flexible. These will all come up later, but there's lots of interesting rigid objects and flexible objects. There's also many different kinds of rigidity. This is the simplest one, and we'll talk about a couple of others. The first other we'll talk about is called generic rigidity. And the idea here is sort of in these top diagrams that most of the time, rigidity is just a property of the graph. It doesn't really matter what the edge lengths are, and it doesn't really matter how the vertices are arranged in the plane. All that really matters is the combinatorics, just the graph, the connectivity. And so the picture is either on the left side, the whole ellipse there is rigid, except for these tiny exceptions, the one-dimensional paths and the points. Okay? Or pretty much everything is flexible, and then there are just these tiny lower dimensional exceptions where it's rigid. And there are a couple of examples of this. If you take the cube graph and draw it generically, you draw it with no 3 points collinear and this sort of thing, it will be flexible. You can try that at home. It's not so easy to see why. But if you draw it sort of in the standard way where all of these lines meet at a point, when you extend them, it's rigid. Here's the opposite example. If you take this is called a Desargues configuration, and draw it generically, it's rigid. But if you happen to draw it with these 3 lines parallel, then this triangle can just rotate over with respect to this triangle. So it happens to be flexible in some special scenarios, but most of the time it's rigid. And so if you're just interested in the generic case, if you don't care about whether exactly this linkage is rigid, but whether something very close to it is rigid, then all you care about is this generic rigidity, and then all you have to do is look at the graph. And generically rigid graphs is one of the highlights of rigidity theory. And one of the characterizations is by Lemon from 1970. And it's this statement here. If you have a graph with n joints, see, I'm supposed to use vertices there, but here I've used joints. And it has exactly 2n minus 3 edges. Okay, the short version of this theorem is 2n minus 3 is the right number. So suppose you have a graph and it has 2n minus 3 edges. And furthermore, every induced subgraph has at most 2k minus 3 edges, where k is the size of the subgraph. Okay? The intuition here is you should have 2n minus 3, but then in every subgraph you shouldn't have too many, because if you had lots and lots of edges in one subgraph, you wouldn't have enough in another subgraph. So if in every subgraph you have at most 2k minus 3, then it's generically rigid. And this is an if and only if for graphs with 2n minus 3 bars. These are called minimally generically rigid because they have exactly 2n minus 3 bars. Of course, if you add extra bars, it'll still be rigid. So here's one example. It's exactly the same as this, but without the grayed out bits. So if you count the edges in this example, it's a pseudo-triangulation, so it better be rigid. It has 8 vertices and 13 bars. I'm cheating. And you compute 2 times 8 minus 3, and it should be 13. If you take this subgraph, you get 5 vertices, 6 bars. You keep checking. Everything works out less than or equal to. And so this graph should be rigid. I've just done 3 subgraphs there. On the other hand, if you take this graph from the last slide, which was not generically rigid, but in this configuration it was, it doesn't have 2n minus 3 bars. 2n minus 3 should be 15. Right? I can still multiply 13, thank you. So it doesn't have enough bars. And so it's definitely not generically rigid. Okay, so that's minimally generically rigid. If you want to do the general thing, you just say, well, you can add extra bars, it's still generically rigid. Okay, you can say it in this lengthy way, or just, the key point is to characterize minimally generically rigid, and then you can add extra edges. Big open problem here is to characterize the 3D generically rigid graphs. So that only worked in 2D, and you can generalize Lemann's theorem to 3n minus 6 in 3D, and that's a necessary condition, but it's not sufficient. And this is one example of a linkage in 3D. Hopefully you can visualize it. So the dots are smaller and larger to tell you sort of how close they are to you. There's 1 degree of freedom here. You can rotate about this pink dotted line, but it satisfies the Lemann condition. Problem here, does anyone know why this is yellow as opposed to all my other figures? I think it's my only yellow figure.
Someone else drew it.
What's that?
Somebody else drew it.
Somebody else drew it. Oh, so cruel. I know, this one looks so good, it can't be done by me.
It goes banana yellow.
Bananas are yellow. See, the rigidity theorist knows this is the double bananas example. It's not my joke. So. Anyway, nice open problem. In all of these lectures, we're going to try and give lots of open problems. This is the first one. Another kind of rigidity, which is quite useful, is called infinitesimal rigidity and infinitesimal flexibility. This is just considering sort of first-order motions. It's just like how to get started moving in the first order. It may not totally work out, but at least it looks like a motion. So, I mean, the cleaner way to say it is, if you have a motion, if your linkage is flexible, then it actually has a smooth motion. Because the configuration space of a linkage is pretty nice, if there's a motion, there's a good one, a pretty one. And so it's analytic. You can take derivatives. And if you take the first derivative, just at time 0, just at the very beginning, you get what's called an infinitesimal motion. So another way to say it is for each vertex, you specify a velocity vector, which says which direction that vertex is going and at what relative speeds those vertices are going. And the constraint you want is that whenever you have a bar between 2 vertices, its length should stay the same to the first order, because you're only defining a first-order motion. Okay, so if, it turns out the equation is this. So xi here is the location of vertex I, xj is the location of vertex j, and vi and vj are the velocity vectors. If you want to measure the first-order change of this length, you just project these vectors down onto this bar, or the extension of that bar, and the projection is exactly this dot product. So you get the dot product of this vector and that, and the difference between those 2 vectors. And that'll tell you how much that edge is changing, and if you don't want it to change at all, you should set it to 0. So it turns out to be fairly simple. This is a linear constraint where the xi's and xj's are known values. That's where you currently are. And the vi's and vj's are the variables. And so you get a linear system. This linear system is called the rigidity matrix, has lots of neat properties. But that's all I want to say about it. Is this slide clear by now? This is a bit bizarre, let's say. You might think that infinitesimal, oh, I'm going to get it backwards. It's very easy to get this backwards. The right way is that if you're flexible, you're also infinitesimally flexible. If there's a motion, there's also a first-order motion. The contrapositive says if you're infinitesimally rigid, you're rigid. So infinitesimal rigidity is actually a stronger property than rigidity. It says not only is there no motion, but there's no first-order motion. And you can look at either the right-hand diagram or the left-hand diagram. Don't cross your eyes. It won't make anything three-dimensional. And it's sort of very clear nesting, let's say, in terms of motions. In order to be flexible, you have to be infinitesimally flexible and second-order flexible and third-order flexible and so on infinitely many times. Then you get a real motion if you're analytic. Or you're infinitesimally rigid. On the other hand, if you're not, let's see, this is saying if you're not infinitesimally rigid, you're infinitesimally flexible. Here you could say, well, there's actually several levels of being infinitesimally flexible. I could be, sorry. No, this is actually infinitesimally flexible. All of this stuff is infinitesimally. That's why this is really hard to see. These are actually to scale. So this box is equal to this box. Okay. You don't have to understand the connection between the left and the right-hand side. Each one is easy to understand. The connection is a little subtle. But not only could you be rigid, but you could be third-order rigid or second-order rigid or infinitesimally rigid, and these are various stronger properties. Good. I think I'll go on from there because it's just confusing. You can generalize even more, and instead of looking at bar and joint frameworks and these linkages where every edge has to stay the same length, you can add two different kinds of objects, struts and cables, and this is called a tensegrity. A strut, I don't have any good examples of struts. Well, here's a strut, my cell phone antenna. It can expand, but I can't get any shorter than this, okay, without breaking it. A cable is like this here, if you can see this cable. It can get shorter, but it can't get any longer. Okay, so I mean, you can think of this as a piece of string. This is like a strut in construction. So while bars have to stay the same length, struts and cables can change in length in one direction. And you can't quite see the notation. The double dashed lines are the struts, and the single dotted lines are the cables. This is roughly the standard rigidity notation. You can define rigidity and generic rigidity and infinitesimal rigidity for tensegrities too. They make sense. These are some examples, some of which we'll see later. If you take a polygon of bars and add struts between everything else, it's flexible. If you take a pseudo-triangulation, remove one edge and add a whole bunch of struts, it's flexible. These are a couple other examples which I don't fully understand. This one is flexible, this one is rigid. This is from an old paper of Bob Connolly's. You can keep going and make fun. There's something called tensegratoi if you want to play with this in 3 dimensions. Let's see. So with tensegrities, and in particular infinitesimal motions, you get a connection to linear programming. And that'll be useful because then we can use linear programming duality and learn something from it. So we used to have this constraint, this linear equality, that the bar length should stay the same. Now we get some inequalities that say that this edge length should only increase and this edge length should only decrease for the struts and the cables. So this is a linear program. It's really a linear feasibility problem because I don't have any objective. I just want to find some motion, some VIs, some velocity vectors that satisfy these constraints. So we can apply linear programming duality. How many people here know linear programming duality? Or maybe I should say, how many don't? A few, OK. No, this half of me knows it, and this half of me doesn't. So you can apply duality, and I won't go through the math. It comes out to something called equilibrium stresses. And duality tells you, if you look it up, I had to look this one up, that if your primal linear program is infeasible, your dual is either infeasible or unbounded. And in particular, this dual problem will actually it will always be feasible. And so that'll tell us it's unbounded, so we'll get to what that means. Let me tell you this dual problem of finding equilibrium stresses. A stress is just an assignment of real numbers that could be positive, negative, 0 to each of the edges in the framework, so all the bars, all the struts, all the cables, so that they're non-negative on struts, non-positive on cables. Bars, they can be anything. And you satisfy equilibrium. So if I take the sum of the forces, so I should say a positive number corresponds to this edge pushing on the 2 incident vertices. A negative number corresponds to that edge pulling on the 2 incident vertices. 0 means you don't do anything at all. And then you should satisfy equilibrium. So if you add up all the forces on this vertex, it's stationary. That's called an equilibrium stress. And if you work out what that inequality means, it says if you have an infinitesimally rigid framework, then you have a non-trivial stress. So there's always the trivial stress. If I put zeros on all of the edges of course, it's equilibrium. It's in equilibrium. The interesting case is when some of the edges have non-zero stresses. And so this tells you if you're rigid, then there's some equilibrium stress that exhibits that you're rigid in some sense. Okay, sort of as usual in rigidity theory, the converse does not hold. So let's look.
So how do you think? Do you think you put the equilibrium stress by just trying to stress it, and it doesn't move?
Yeah.
It's an equilibrium it can't move? Or?
Right. So an equilibrium stress is like the edges are pushing and pulling, and yet nothing's actually moving. So that sort of feels stuck. Okay, it doesn't actually imply rigidity, but it implies that at least a piece of the linkage is rigid. So what an equilibrium stress somehow tells you, you have this local rigidity. And one way to formulate that is this theorem that if you have a stress that is non-zero on a strut or non-zero on a cable, then every motion preserves the length of that strut or cable. Okay, so a strut would like to be able to increase or stay the same. If there's a stress that is non-zero on that edge, then it has to stay the same. So it acts like a bar. So that's sort of a converse in the context of tensegrities. And you can say, in general, your tensegrity is infinitesimally rigid if and only if there's some stress on all the struts and cables. And if you turn all the edges into bars, then it's also infinitesimally rigid. So this gives you another way to test infinitesimal rigidity. So this is stresses. Stresses are cool. One way in which they're cool is this theorem called the Maxwell-Cremona theorem. This is from the 19th century. Of course, before all of these terms were developed. But so this is another way to look at a stress. It's kind of nice. It talks about polyhedral liftings, where you take your graph and it's in the plane. So this, but I'm drawing in 3 dimensions. And I take each of the vertices and I assign, I'm in the US, a z-coordinate. And so, for example, I could lift this vertex up. And I get now this triangulated terrain. And the property I have here is that all the faces stayed planar. Well, they were triangles, so of course they stay planar. But in general, you could try to lift a vertex, and not all of the faces will stay planar. So here, one of them is a triangle, and so everything's OK. The quadrilateral face back here sort of gets bent. OK, so this graph has no polyhedral lifting. This one does. And the Maxwell-Cremona theorem says you have a lifting other than the flat one if and only if you have a stress other than the 0 one. And in fact, 0 stresses correspond to flat edges in the lifting. Positive stresses correspond to valleys in the lifting. Valley is like this. And negative stresses correspond to mountains in the lifting. Okay, so it's just sort of a more geometric interpretation of these numbers. You have to work out that equilibriums in the stress correspond to exactly this lifting being planar. Okay, it shouldn't be obvious from looking at it, but it's a very nice property. And that's it for rigidity. Any questions before we move on? Yeah. Simple graph that's infinitesimally flexible but not flexible. Hope I can get this right. I feel like I'm taking an exam or something. Let's see. Good. These triangles make the whole thing rigid. This vertex can move infinitesimally that direction, and these edge links don't change. But you can't actually move this because the whole thing is taut. It's generically flexible, but in this particular configuration, it's not flexible.
So what's
Yeah.
flexible about it?
It's infinitesimally flexible. If you look at the change in this edge length in projection, this is 0. This vector is 0. And so this edge length is staying the same, even though this guy's moving and this guy isn't. So you can infinitesimally think of this as you're rotating around this circle. And to the first order, you're just going straight up. And so locally, everything looks great. So this is infinitesimally flexible.
How is that generically flexible?
I'm guessing. I don't think. Oh, maybe not.
I don't think so.
You're right. You're right.
You still have the 2 triangles.
Yeah, yeah. So this is generically rigid even. Good. Yeah.
So it's not clear to me why every graph should be either generically rigid or generically flexible. Like in principle, you have different full dimensional components, which are in the normalization space, right? Is there an obvious reason why that can't happen?
Yes. I'm not sure that I know it though. So it's something about being algebraic. I mean,
so it's like zero sum algebraic equation.
right. So this space of this configuration space of the linkage is an algebraic space because it's just you're specifying a bunch of distance constraints, quadratic equalities. So you know it's an algebraic set, so you know it behaves nicely, and it's sort of like in a geometric setting, a theorem is either how's it go? It's either always false or almost always true. So it's something like that.
That's over-complex, we are over the wheels.
Yeah. So here you can get sometimes it's almost always true, and I'll get it backwards.
Only if there's a sign to that.
All right. So you guys know algebraic topology better than I do.
Well,
So.
the dichotomy is strange.
Algebraic geometry.
If it were just simply like some set of equations vanishing, then for determining whether it's flexible or rigid, then you'd be able to.
So the issue here is whether.
It's either generically flexible or generically rigid, requires a little more.
Yeah. So the issue here is whether the rank of this algebraic system goes down. That's somehow what's going on. If you look at a little ball around your configuration, and I don't know enough algebraic geometry to prove that, but I assume if you did, it would be trivial. So that's why I said yes. Other questions? Yeah.
I'm apparently misunderstanding something in your diagram. Why is it that little vertical line at the bottom? Imagine that you thought of that as a hinge.
Yeah. Oh, in 3D, this is flexible.
Sure.
It's just in 2D that it's rigid. So if this is a hinge, yeah, it'll probably flex. Okay, I'll move on. The next topic is locked chains and trees and various objects. This is sort of an ongoing quest over the last 5 years or so. It's pretty much done, although there are a couple of open problems. Lots of nice results. The general question is, I give you 2 configurations of the same linkage. Can you get from one to the other? Always. So in other words, is the configuration space connected, or is the free space connected? I'm only interested here in non-self-intersecting motions. Another way to ask the same question is, can you get from any configuration to some canonical configuration? Can you unfold any linkage of a particular type? Because if you can get from everywhere to there, you can concatenate motions and play them backwards and get from anywhere to anywhere else via this canonical state. I call this the FedEx algorithm. The founding idea of FedEx is you ship all packages to one place and then send them out to where they actually belong. This idea is used all over mathematics. So what does canonical mean? Well, for arcs, I want the straight configuration where every vertex angle is 180 degrees. For cycles, I'd like a convex configuration where every interior angle is less than or equal to 180 degrees. There are several convex configurations, but it's pretty easy to show that once you get to convex, you can go to any other convex configuration, even staying convex. And for trees, I'd like something called flat configurations, where all the vertices lie roughly on a line and all the edges point to the right. And so for each of so you could also go beyond trees, but trees are already hard enough, so we don't go to more general graphs. For arcs and cycles and trees, you can ask whether every arc can be straightened in 2D or 3D or 4D or higher. 4D turns out to be the same as everything beyond, because these are sort of one-dimensional structures. Cycles, can it be unfolded? And trees, can it be unfolded? Some of these problems are pretty old, like 30 years or so, and then were solved in the last few years. Probably the most intuitive column is this one, because if you know some knot theory, you know that there are knots in 3D, but there aren't knots in 4D and higher. And also, there aren't knots in 2D. That's pretty easy.
That would be the cycles column.
Cycles, thank you, yeah. Same thing. Yeah, in fact, there are no knotted arcs anywhere, so this is not so intuitive. Okay, so that's the intuitive column. You'll see in a moment why arcs are almost the same as cycles. That's why I said they're the same thing. Trees, however, behave very differently. So even if you allow 1 degree 3 vertex in a tree, you can get locked trees. So a tree that cannot be flattened in the plane. And that's a hint that 2D was actually the hardest of these problems in some sense. And so these were the cells that were last to be filled in. I want to talk about these cells, and then this one, and then these two. Okay, if you can remember that. So let's start in 3D with arcs and cycles. This is one of the earliest notions of linkage folding in 3D. This is called a knitting needles example. You take 2 really big knitting needles and knot the string. It's not really a knot topologically, but geometrically you just can't escape, because in particular there's this sphere that separates these vertices from these vertices. No matter how you reconfigure this, you can never get these vertices inside the sphere or these vertices outside the sphere if you make the sphere track these guys, if you make the sphere the right radius. And so that proves you might as well just connect these ends with string, and then it's a knot, and you can't untie the knot by continuous motion without self-intersection. Okay, so that's a locked 3D chain. Open chain, an arc, if you want to make it a cycle, you just double all the edges in this way. Now you have an unknotted cycle. So topologically, you can still go out to a loop. But geometrically, it's stuck for exactly the same reason. There's actually simpler cycles. You can get at locked hexagons. I think currently there are exactly 2 known classes of locked hexagons in a certain sense. It's open whether there are more. So it's a little puzzle for you to make. In fact, this was the original example of a locked hexagon, and then Godfrey Toussaint tried to build it but made a mistake and found another class. All right. That's the very short 3D story. There's lots of other things here, including an Erdős problem and so on. But I want to go to the plane. Here's a tree that's locked in the plane. Here I have 8-fold rotational symmetry. There's 1 degree 8 vertex in the center. It's connected to 8 petals. A petal is a 3-bar arm that sort of wedges into the center. And the idea here is that if I try to open up one of these petals, which is necessary for it to flatten, there isn't enough room. This bar will bump into this bar. If I draw this picture sufficiently tight, it's a bit spread out here, so you could probably do it. But these are really tiny distances, and so you can't open this out. The only way you could open this out is if somehow you could open up this angle. But you can't open up any of these angles without closing another angle. And you can't close an angle unless you've opened up a different angle. So you get this chicken and egg scenario where nothing can happen first. The details of this proof are much messier, I must say, that we don't really have good.
You did them all at the same time.
No, it doesn't work. No one can be at the first time. It's not that no one can be first. Yeah. Sorry, it's locked. Actually, there's a couple of proofs of this by now. You can prove that in a certain sense this is infinitesimally rigid, which implies that it's rigid, and so on. So there are now some fancier techniques, which I forgot about when I was making this slide, that you can prove this even computationally completely automatically you can prove that this is locked, which is kind of nice. But I want to talk about the arcs and cycles in 2D. So a natural thing, which actually several notable mathematicians who I will not name have tried, is to take this tree, which is locked, and double every edge and make it into a cycle. Now this cycle is arbitrarily close to the original tree, and so the configuration space should look almost exactly the same as the original tree. And except for that point, right? The catch is that this used to be 1 vertex of degree 8, but now it's 8 vertices of degree 2. And the new motion in this cycle is you can separate them. And you get something like this. So you blow up this central star, and then you can unfold the arms, and you're done. So it's a bit subtle, the difference between arcs and cycles. This should also give you a hint of why it was tricky to prove that cycles can be blown up convex. because you really need to move lots of vertices at once. And so for a human to do this is quite tricky. You have to look at these very strange motions. We did it for some years trying to find, we tried to find examples that were locked, but then we kept opening them. Eventually we proved that they're all openable. So I want to give you quickly the proof of that theorem because it's not very hard, given all the stuff that you've learned in the last 45 minutes. So one of the key ideas is to look at expansive motions. This is sort of a reformulation, but it was a big eye-opener somehow. If you constrain, these are just two random bars in your chain. If you constrain that the distance between all pairs of vertices increase, then in fact the distance between any vertex and any bar cannot increase by the triangle and cannot decrease by the triangle inequality. And so you can never get a vertex crossing a bar. So if you could guarantee this expansive property that every pairwise distance expands or stays the same, in particular you'd avoid crossings. It's sort of overkill. But expansiveness, you should start to think of struts or something. So this is going to connect to rigidity and tensegrities, whereas crossings are very tricky to capture because they're non-local. This will sort of make it much more finite, much more combinatorial to look at just pairs of distances. So the theorem is not just one cycle, or so the chains there should be arcs. It's tough to stick. You take any collection of open and closed chains or arcs and cycles. There's a motion of all of them together that avoids self-intersections. It increases most of the distances. It keeps the others the same. Straightens the arcs, convexifies the cycles, except that if you have an arc or a cycle contained within another cycle, once that cycle convexifies, it stops moving. Everything inside here can't expand anymore. So we allow this kind of configuration, but you're only guaranteed that the outermost objects actually straighten and convexify. So this is, by now, an old result 3 years ago with Bob Connolly and Günter Rothe. You have other nice properties like you preserve symmetries. It's piecewise differentiable. Why don't I show you some animations just for fun? Take a little break. Here's that double. This is a slightly different doubled tree, actually, but same idea. It's not the tree, obviously, so it's not locked. It's just a polygon. It has to load the animation. And this will be the expansive motion that comes out of this theorem. And so it preserves a five-fold rotational symmetry, all sorts of good things. Here's another example. This is probably the first example of this problem that I saw as sort of proposed to be locked, although it's not so obvious. The tricky thing here is you cannot pull the teeth straight apart because they'd self-intersect, but you can unroll them. I won't tell my usual bad joke about this example. And here's an example with a few pieces. It's got one central polygon and 4 arcs on the outside. Okay. So that was just for fun. Let's prove the theorem. It's pretty easy once you know how. We're going to make this object as a tensegrity, as I alluded to before. We've got all the bars. Let's just add struts everywhere. And these struts represent that I want an expansive motion. Now, all I care about is whether this tensegrity is flexible. Just have to prove that it's flexible. And we've got all these tools for proving that things are flexible. One way to prove it's flexible, a bad way to prove it's flexible, is to prove that it's infinitesimally flexible. That's not enough in general, but it will be enough here. So leave that for you to think about. We'll get there. We need to do one other modification, which is to make this graph planar. It's not very planar. It's the complete graph. So we're going to cheat and add vertices at all the intersections. Wasn't that easy? And then sometimes we have repeated edges. Here there's 2 struts. I'll replace that with 1 strut. And here there's a bar and a strut. I'll replace that with just the bar, whatever's the strongest constraint. And so, boom, they're gone. Now I've got a planar framework. I need a planar framework because this thing about polyhedral liftings only worked for planar frameworks. I didn't mention that. And now, here is the proof outline. We need this last step. I want to prove just for now that the framework is infinitesimally flexible. I claim that's enough for what I need. And duality told us that it's enough to prove that you have no equilibrium stress, that the only equilibrium stress is when I put 0 on all of the edges. You remember, if it's rigid, there is a stress. So if I prove there's no stress, it's got to be flexible, infinitesimally. This is equivalent. This arrow should actually go both ways. There's a stress if and only if there's a lifting. And so I just need to prove that there's no lifting. Whoops, sorry. That's here. OK. The other modification I did is I added these extra vertices. And when you add extra vertices to a linkage, conceivably you get extra degrees of freedom in the motion. Turns out you don't. In terms of stresses, the original framework and the planar framework behave exactly the same. Okay, I won't prove that because it's just tedious. It's not very interesting. And finally, now we have a planar framework where we can use this Maxwell-Cremona theorem. And all we need to do is prove that there's no lifting. And now, what's nice about all of this work that we get for free from all of these known theorems is it's purely a geometric thing. We can talk about these polyhedral liftings. Suppose we had one, look at its structure, somehow get a contradiction. We want to prove that it's flat. OK, so here's the idea. What this geometry gives you is you can look at things like the topmost extreme, what the maximum z-coordinate is in this lifting. So that it could look anything like this, pretty much. You could have, this is like a mountain peak. It comes to the very top. This is a slice at the very top. So if you just get a point there, everything could go down around it. I think that's what I'll draw here. So you have one point, and everything is sloping down from there. One thing that you know is that this represents that this whole region is at the top, whereas here the exterior is at the top. You could have any of these cases, conceivably. These edges are actually mountains in this polyhedral lifting, right? One of them is flat, and the other one is downhill, so this is a mountain. And you may recall from way back that a mountain in this lifting corresponded to a positive stress in the equilibrium stress. And if you remember even farther back, a positive stress can only be carried by a bar or a cable, not a strut. And in this configuration, there are no cables. It's just bars and struts. So these mountains actually have to correspond to bars of the linkage. OK, sorry, you have to recall so far back. Now, the bars in this tensegrity are just the original things, the arcs and the cycles. We only added struts. So each of these edges on this maximum extreme of the polyhedral lifting have to correspond to bars. That's basically the key. So now if we look at, for example, this configuration, which I claim cannot happen, all you have to do is slice that polyhedral lifting just below the maximum z-coordinate. You get a polygon, this red thing. And you know that wherever you have a convex vertex in this planar polygon, you have a mountain in the lifting. And wherever you have a reflex vertex, you have a valley in the lifting. And you know that every polygon, hopefully you know, that every polygon has at least 3 convex vertices in the plane. And that corresponds to 3 mountains in the lifting, and that corresponds to 3 bars, all incident to this vertex. But that means you have a degree 3 vertex, at least in the original linkage, and you don't. It's all maximum degree 2. OK, that's the heart of the proof. It gets rid of this particular case. The other cases are similar. Yep. Maybe it's not enough. The other cases you can cover with this slightly more general lemma. It says that if you look at a particular vertex, this is just in the plane, it's got maybe 2 bars, and everything else is struts. And if you look at these 2 bars form a convex angle on one side, a reflex angle on the other side. If you look at this reflex angle, this pi wedge here, this Pac-Man shape, I claim all of it has to be at the maximum z extreme. If I could prove that, it would throw away something like this picture, because here I have a reflex portion between 2 bars that's not at the top. Black means not at the top. So that's no good. This is also not valid because, again, I have a reflex portion that's not at the top. The only thing that could happen is if I have a convex polygon surrounded by stuff at the top. But if everything's convex, I'm happy. So this would be enough. It would eliminate everything except the good case when we're done. To prove the lemma, it's basically the same. You slice just below the vertex. You now don't get a polygon. You just get a polygonal arc that connects this bar to this bar. And again, to go around a reflex corner, you've got to have a convex vertex. That corresponds to a bar, but you already had 2 bars, since you've got 3. Okay, same idea, just slightly more general. And that proves that this tensegrity, where I take a polygonal arc and maybe a polygonal cycle or a bunch of them, I add in a whole bunch of struts, it is infinitesimally flexible. But you may recall that infinitesimally flexible is not enough to be flexible, and so you need a little bit more work. I don't want to go into the details because they're not too interesting. You basically pick some canonical infinitesimal motion by, say, adding an objective function to the linear program, making it strictly convex. And that'll tell you, it gives you a differential equation. At every point, you know to the first order which way you should go. And because this set of good configurations where you always know which way to go is a nice, happy, open set. Happy is not the technical term, but it's sufficiently continuous and, well, or sufficiently compact and whatnot. Maybe you just need openness. And because it's continuous, if you define it in the right way, general theorems in ordinary differential equations tell you there is a motion. And that's it. You can do fancier stuff. You can get Lipschitz continuity if you know these things and get a canonical motion that proves that the configuration space is contractible and all sorts of great things. But this is the simple version. Good. Running low on time. So
the key thing, though, is the conditions. You need to have a reflex vertex in order to be able to actually
right.
solve and continue the differential equation.
Yeah, right. You have to have, for this infinitesimal motion to exist, you have to have a reflex vertex in an outermost cycle or arc. Yeah. Other questions?
Is that how the movie was? How the animations?
Yeah. So that motion is just those animations were just from. We'll get to algorithms in a moment, but that was just you solve the ODE by some simple approximation. At each step, you solve this linear program or quadratic program to tell you which way to go. You move a little bit in that direction, and you get these cool animations. What's funny is we had in mind this algorithm for some time. We never implemented it until we proved that it worked. It would have been much more satisfying to see the animations then, oh, it must work, and then prove it. But for some reason, it never occurred to us. We computed one infinitesimal motion, but we never pieced them together to see the whole thing.
Maybe you're nervous about actually taking the time to program it.
Yeah, it did take some time to program. Yeah. What's that?
If you don't prove it first, then it doesn't.
If you don't prove it first, it doesn't work. Okay. I guess you have a choice whether I go very quickly through algorithms or very quickly through protein folding. Let's have a vote. Well, maybe I want to decide. No, I should let you decide. How many people want to see algorithms in more detail? Okay, it's like those are the computational geometers in the group. And how many people want to see protein folding? Okay, protein folding wins. That would have been my choice too, so I'm glad. Very quick, here is the short story of algorithms. There are 3 algorithms currently. The original one, which I showed you, one by Stranu at almost the same time, based on pseudo-triangulations. Very cool if you know pseudo-triangulations. And a new one called the energy method. That's it. Let's see. This one preserves symmetry, so does this one. This one doesn't. This one's really hard to compute. This one's pretty hard to compute. This one's damn easy to compute. That's the contribution here. For some notion of damn easy. You have to define that very carefully. There's still open problems here, like whether you can do it in time polynomial in the input size. Currently, only this algorithm is strongly polynomial in the output size, but the output could be quite large. So we don't have any really good bounds on the number of steps you need, in some sense, to unfold these things. Yeah. This is the energy method. Isn't that cool? The idea is very simple. You define an energy function like 1 over the sum of the 1 over the distances squared. And this energy function has the property that when you get close to self-intersection, the energy shoots to infinity because the distance goes to 0. And we call that the charge property. And the other thing is that if you have an expansive motion where all the distances are increasing, then the energy goes down. And we know that expansive motions exist. So we know that there's always some downhill energy flow. Let's just pick any one. Let's follow the gradient downwards, for example. That gives you a motion. It can't self-intersect because you don't go to plus infinity by going down. You start finite, and so and you need some other minor properties, but basically from that you get a motion. It's not expansive anymore, but it's very simple to compute. It's just gradient descent or conjugate gradient or whatever. Can this be used to prove the existence of a motion? We don't know.
Well, no, you might end up in a local minimum and you can't go any further.
Right, so we don't. It would be nice if there was some other way to prove that there's always a downhill motion, but we don't know such a proof. Let me show you an animation. It's the fun part, right? 2 animations. These are scaling out, so you're zooming out as they get bigger. Okay, that was fun, yeah. These are easy to compute. You know, it took less than a minute to compute these, whereas the other examples I showed you took many days to compute. They look different. The top one is the original method, CDR, and the bottom one is energy. This one's somehow more balanced. I don't know. Sort of keeps things more spread out as much as possible. Good. Those are the ones I showed you. Let's go to proteins in my remaining -1 minute. So proteins fold. Proteins are these strings of amino acids. There's like 20 different. There are exactly 20 different kinds. They follow some energy behavior, and they go to usually a unique optimal state. Very cool. They do it quickly. No one really understands how or why, and that's the protein folding problem. Proteins are complicated. That's the point of this slide. And they're important. We care about protein folding because if you could understand the geometric nature of protein folding, it gives you some notion of what the protein is actually doing. In fact, if you can analyze the rigidity and which parts are flexible, you get some notion of what this protein mechanically does, and various people do that. Why do we care about actual protein folding? Or why do we care about what proteins do? Well, if you look really close in any part of an alive thing, there are proteins there. They do stuff, usually right, sometimes wrong. Protein folding mishaps are somehow the cause of many diseases. You can pick your favorite disease here. And so maybe we could cure these diseases if we knew how to build proteins that folded into particular ways to disable bad proteins or somehow to fix existing proteins. Lots of interesting questions here. You probably know protein folding is important. There are also lots of cool linkage folding problems, just pure mathematical linkage folding problems that come out of protein folding. So one model is the fixed angle linkages, where in addition to an edge length staying the same, you also constrain that the angle stays the same. So then all I can do with my arm is spin it around here. I can't change this angle. A protein is roughly a fixed angle tree. And one nice question you can ask is if you look at all of the flat states, all of the flat configurations of a fixed angle linkage, when are they all connected by motions? That seems to be a key question about flexibility. You can't hope to get a connected configuration space, but you could at least hope to get the flat states connected. And we don't even know whether all trees have this property or whether all fixed angle chains have this property. Okay? We do know some special cases like non-acute chains where all the angles are bigger than 90. Or if all the angles are equal and acute, we can do it. But for trees, we don't know. For planar graphs, the answer is no, you can't always do it. So there's a lot of interesting open questions here.
If all the angles are fixed, how can it move them?
In 3D. Sorry, we're in the 3D world here. So that was the example where if I fix this angle, I can still spin my arm this way.
But you're changing the
I'm keeping
shape
this.
of your shoulder now.
Sorry, this is a 2-bar linkage. It doesn't include my shoulder. Let's see. I could still do something like this. That should be rotating about my shoulder.
Oh.
You get the idea.
You
You can
combine
also
the
still
third
do
part,
this.
You're still not changing the angle.
We're changing dihedral angles, but not the edge-to-edge angle. The interior angle, whatever. Okay, another model, which is maybe more surprising, if you just look at the backbone of the protein. So a protein is roughly a chain with little strands hanging off, like a caterpillar graph. The backbone actually has enough flexibility that it's pretty much like, it pretty much has all the motions that my, okay, maybe you can perturb it a little bit. And the hard part here is to make it unique. So I don't want to fold into that shape in particular. I want it to only fold into that shape. What's that?
So that it actually does fold into that shape.
So it does fold into that shape and only folds into that one. This is kind of like drug design, but in a very simple model. But it would be a start. And seems cool. I think that's it. Thanks.
Any questions?
Yeah.
Have you tried your energy minimizing algorithm on that equal length 3D chains?
Yes. No. One of the two. So the question was, this equilateral 3D chain problem, could you apply like the energy minimization method? I have tried applying expansive motions, and those don't work. So if you take the knitting needles and then shorten everything so that it's equal length, that thing can be untied, but not by an expansive motion. I haven't tried it with energy. It's conceivable energy finds a motion. It's a good question. I should try it. It's easy enough to implement energy in 3D. So, other questions?